All right. Hello, welcome to the virtual RIT Research Symposium. I'm Tristan Smathers, an active participant in the RIT REU C-STEP program. And this is my presentation, Manufacturing for Marketability, the Organic Solar Cells Journey to Industry. My advisor is Dr. Christopher Collison, head of the Collison Research Group, and we're going to be looking today at organic photovoltaic cells. So first, I'm going to introduce the problem at hand. I want you guys to know why this all matters. So what's happening currently in the world is that we are using an extensive amount of fossil fuels, and these are creating a lot of greenhouse gas emissions, and this is aiding into the problem of climate change and really leading to spiking temperatures worldwide, melting ice caps, and we're also amidst an energy crisis. And this is really honing in on the real problem, which is a dire need for renewable energy. We need to be getting our energy from sustainable resources other than fossil fuels. And that being said, we'll use resources such as geothermal, wind turbines, but more importantly, the focus of this presentation is solar energy. So the current technology is using silicon modules. These are very expensive modules that common people can't really access as easily as they need to, and they're very energy consuming when it comes to manufacturing processes. A potential solution to this need for renewable energy and escape from silicon technology is organic photovoltaic cells. And today we're going to be going over the barriers to the commercialization of these organic photovoltaic cells. So without further ado, let's look at the market needs, the opportunities and values that OPV offer prior to looking at their barriers. So we need to be able to industrially process these cells with a method known as roll-to-roll printing. This is very necessary in order to keep up with the rapid rate of manufacturing in order to produce enough cells for this to be a profitable business and also a low-cost alternative to silicon. We also need to be using flexible and affordable materials. One advantage of organic photovoltaic cells is their ability to be implemented into infrastructure and odd projects that silicon modules are not very commonly used for, and that makes it very appealing to architects and different industries. As well, we want to be able to provide the less fortunate with the means for electricity. There are currently 1.3 billion people without electricity in the world, 6 million of which are in Africa, and organic photovoltaic cells are really an up-and-coming technology that offer a low-cost alternative. And speaking of low cost, the lower cost manufacturing is going to create an appeal for consumers, distributors, producers, and all the like. Now, if you look to the figure at right from a Krebs paper talking about roll-to-roll processing and manufacturing of cells, we have something known as the unification challenge. Now, process, stability, and efficiency are all three mainstays in OPV technology production. And where they meet in the middle is where we create an ideal cell that can be commercialized and sold to consumers. Now, the first barrier that we're going to look at today is stability. So, within the stability of an organic photovoltaic cell, we need to look at how long it's going to last in comparison to silicon modules. And for a metric of comparison, a typical silicon module has a lifetime from anywhere between 20 to 30 years. And that is important to keep in mind when looking further. So why is stability such a paramount factor in OPV manufacturing? We need to protect it against the environment that it is going to be experiencing. Many trials have been done in different environments. More specifically, ones that I've looked at are trials done in Rwanda, which is a very extreme environment, about 2 degrees below the equator. And these cells lasted 1,700, in between 1,700 and 3,000 hours, which is roughly between 2.5 and 4.4 months. Now, this is not really much time in comparison to the silicon module's current lifetime, but it does show that OPVs have the ability to survive in the field. Another trial looked at was a humidity-based experiment for an accelerated lifetime trial, and these cells only lasted 25 hours at a relative humidity of 65% and 850 hours at relative humidity of 33%. And this is making one notion very clear. We need to increase the module stability and how it is preserved against the environment is experiencing. And there is a solution to that that we can factor in at RIT. And that is going to be encapsulation. So at right, what we have here is a single module from the Rwandan trial. These were put into a village in Kagano. And below what we have is 3 of these exact same cells post-trial. And they were exposed to a very intense environment, high heat, even a fire and ash cover, lots of moisture, and a very dry and arid environment nonetheless. So encapsulation is done in order to protect the cell from the environment. If these cells were not encapsulated, and to make note, they were encapsulated using hot melt office plastic, which was not a specialized encapsulant by any means, they were still able to survive for about 2.5 to 4.5 months. Now, The styles of degradation are happening via light, photooxidation, so the light coupled with oxygen coming into the cell, and as well moisture seeping in through tiny holes where these contacts are. Otherwise, the cell is completely sealed off from the environment. And this is making one notion clear. This degradation and delamination is creating problems within the cell, and we're going to have less power conversion efficiency when these things are affected. So what we need to focus on is making a better encapsulant that is going to promote a better lifetime and power conversion efficiency in the long run. Next up, we're going to look at the process of organic photovoltaic cell production. At left, what we have here is a figure of roll-to-roll printing, and there's going to be two different methods by which this is done. It's going to be the discrete method, which is going to involve multiple steps, and the integrated method, which is going to involve multiple steps, but they're done seamlessly on the same printing press. So what occurs within these is this thing right here is going to be called a roll, and it's going to be splayed out into another roll across it, and this is going to be called the web. And we're going to deposit different layers of materials that create the organic photovoltaic cell. And in the discrete method, we're going to do one step at a time and then move the roll to the next step. And that's going to be less efficient when it comes to manufacturing, but sometimes it's necessary when production is occurring. And the integrated is going to do all the steps simultaneously, which is very efficient. So one thing to make note of is that organic photovoltaic cells must be produced using these industry adapted means. Otherwise, we can't keep costs down and we can't offer these to consumers at a reasonable rate. And that makes it really worth producing, is keeping this cost down. Now, to make note, lab-based experiments that produce these cells without the consideration of roll-to-roll processing being a need they feel as if they are an issue because we are looking to be able to produce these cells. And if a cell can be creating a high power conversion efficiency, that is great. But we also want to be able to sell this to a consumer. Now, when you look deeper into roll-to-roll printing, sometimes there's going to be different nuances, steps, and processes that present manufacturing issues. And that could be anything from annealing, which is going to need a whole different step, which is why the discrete process is mentioned, and as well solvent additives that need to be evaporated. So this is going to create different problems when it comes to manufacturing cells using different materials. Now, we're going to bring up methods for comparison between the lab scale procedures and roll-to-roll. So first, what we have here is spin casting. Now, spin casting is typically used in laboratory instances, and this is what's done to create a thin film over the substrate layer of plastic. And this man here is going to drop deposited ink with a pipette onto the spin cast. This is going to be spinning or rotating, and the angular velocity is going to evenly distribute the ink layer to create a thin film. Now, this is very efficient when it comes to creating uniform cells, but these small area cells may have a very high efficiency, but this method is not adaptable to the industry. And what we need to know is, so how can we perform experiments in the lab that lead to an industrial scale operation? So without any further ado, what we have here is 4 methods of roll-to-roll printing discussed in Krebs' paper. Now, this paper here has knife over edge printing, slot die printing, gravure printing, and meniscus printing. But I want to look further into knife over edge printing because we have the ability at RIT to use a deposition method called doctor blading that is very close cousin to knife over edge. The other methods are also very useful, but at RIT, we are going to find it very efficient to focus on translating to knife over edge printing. So next, we're going to look into the efficiency of these cells and how we can create a better relationship for them. So in an organic photovoltaic cell, there is a relationship between the donor and acceptor with translating electrons. And so the HOMO and LUMO stand for the highest occupied molecular orbital and the lowest unoccupied molecular orbital. And these are going to create a relationship between the donor and the acceptor that creates energy. So what's going to happen in this relationship is that light is going to shine upon the donor. And an electron right here is going to be excited and travel to the LUMO of the donor. And what would typically happen is that leaving the excited state, it would travel back down to the HOMO of the donor. But in this relationship, the electron then travels to the LUMO of the acceptor. And then it will then travel back down to the HOMO of the donor. This is going to create the open circuit voltage. This is an energy produced via the electron transfer, and this is going to aid in creating power conversion efficiency for the cell. Now, as you can see, the gap or the band gap between the LUMO of the acceptor and the HOMO of the acceptor is going to be the maximum potential for the open circuit voltage. And by experimenting with different materials that have a larger band gap, we can also create a larger open circuit voltage, especially by reducing the gap between the LUMO of the acceptor and the LUMO of the donor. Now, we need to keep in mind that these materials need to be commercially available, and cost efficiency is definitely a must when it comes to creating an efficient product. And we need to experiment with novel materials that push us towards generating more efficient cells. Without doing this, we are not going to be able to create a marketable product that has the ability to convert power at a rate that we need to compete with silicon cells and fossil fuels. So diving deeper into that, we are going to look at this table here. Now, this is an experiment done with 6 commercially available donors, other than the commonly used P3HT PCBM. And I want to draw your attention to the active layer column. So here we have these 6 commercially available donors, all experimented with PCBM. And I want you to look over to the right to the PCE column that stands for power conversion efficiency. So as you can see, all of these 6 commercially available donors actually outperform P3HT PCBM. And for me, that's saying one thing. Other materials are going to deserve consideration. And in particular, I think that squareins deserve a very big consideration because they're organic molecules and they are not necessarily keeping in line with the polymers that we've been studying through this remote research. And at the Collison Research Group, we are going to be able to look at organic molecule depositions and experiment with these molecules further. Now I want to address my recommendations going forward. So we're going to go over the barriers to commercialization, their potential solutions, and their applications to research groups at RIT. So in order to increase the module stability, we are going to encapsulate cells. This is going to allow for larger lifetimes and a better performance and stability. And the application of the RIT research group is we can use things such as the office hot melt plastic used in the Rwandan trials to create stable squarane-based cells that we can do in-field trials with and gather data. In order to beat the barrier of industrial adaptive processing, we should use deposition methods that allow for an upscale into production process and allow us to translate what we've done in the lab to industry. And how we're going to do that at RIT is by using doctor blades to deposit active layer materials. We can keep up the standard of manufacturing techniques. Now, the last barrier to commercialization is looking at the efficiency of cells. And a potential solution that is to look further into donors and acceptors that are commercially available and able to increase the efficiency by looking at the energy, or looking at the band gaps and increasing the open circuit voltage. And in order to do that at RIT, because the Collison Research Group specializes in squareins, we can do experiments involving that and seeing how they take effect to outperform P3HT PCBM efficiency rates. Now, I'm going to go into what I got out of my 10 weeks. So over the course of my 10 weeks, I've been able to develop my soft skills as a presenter, a communicator amongst the team, and working with an advisor on a research project. I'm an undergrad student transferring to RIT, and without this experience, I would not have gotten the experience of a graduate student until much later on if I plan to take my education forward. Now, throughout these 10 weeks of summer, I've also been able to develop myself academically amidst the COVID pandemic. And while remote research doesn't necessarily seem so enticing, I found myself loving what I've done and really developing myself as a person when I would have been working or mowing lawns or something of that nature. Now, as well, the most important thing to me is that I've written a framework for a publishable report in aid with Dr. Collison and my partner, and I'm going to be a co-author on that paper. And that is something that I'm very proud of and glad to take part in. I'd like to make acknowledgements to the National Science Foundation, and we received our grant funding from the REU site, Materials, Applications, and Development for Organic Photovoltaic Devices, with the grant number NSF DMR 146-1063. And I'd also like to make great acknowledgements to my advisor, Dr. Christopher Collison, an RIT professor at the School of Chemistry and Material Science in the College of Science. He helped me very much so, and it's been a great experience. Thank you all for listening. Feel free to ask questions in the comment section, and I'll be sure to reply when I'm available. Thank you.